Okay, we're continuing our discussion of, about soil deformation. Actually, this is the last screen from the previous lecture. We were discussing the time to reach U% of the final settlement. And the time is given by this expression. Tu is capital Tu HD squared over C sub V. T sub U is the time to reach U% of the maximum settlement. Capital T sub U is the time corresponding to U% consolidation. C sub V is the coefficient of consolidation, and H sub D is the drainage length. And then we discussed the difference in drainage length between one-way drainage, when the water can drain only in one direction, maybe impervious and fill on top, so the water can go this way but cannot go that way. And of course that could be interchanged, or two-way drainage where the water can go up or down. And in this case, the drainage length is 1/2 the thickness of the layer that's compressing. In this case, the drainage length is the full length, full thickness of the layer. By the way, before I forget, there's another problem that's quite good to do, problem 17.11. This is a problem on the magnitude of the settlement. You know, we did an example in the previous lecture. This is another one. We don't have time to do it, but I believe it's part of the assignment, so look at this problem as well. Again, it's on the magnitude of the settlement, not the time of settlement. So back to the time of settlement. Basically what happens is that if you look at settlement here, so we'll call this settlement as a function of time. So this is time, and this is settlement. Then in a case like this where you have a fill, then the curve will actually do something like this. And then the settlement, so this is, if you wish, settlement as a function of time. And then you reach a point here where you have the maximum settlement. So we'll call this S max. And if I plot that curve again by normalizing the axes, I could do here a plot, and I'm going to normalize the time by doing T. I'm taking this equation here. I'm going to do T times C sub V divided by HD squared. So T times C sub V divided by HD squared. So this is time scale, but normalized with respect to the coefficient of consolidation and the drainage length. And then on this axis, I'm going to put S sub T divided by S sub max. So in other words, this starts at 0 and ends up at 1 or 100%. So in this case, I have normalized this curve. And what I get is a curve that looks like this. It doesn't go to 1 because actually it takes an infinite amount of time to be able to reach the maximum settlement. But on this curve, you can see that this is the time factor T. That's in that equation over there. And this is the average percent consolidation. So I should add in here that U is the average percent consolidation. And in that case, we'll take it equal to the settlement at time t divided by the maximum settlement and times 100, because usually when you look at the charts in the book, this U value will vary from 0 to 100%, so 100% or 0 to 1 if you just take it as a ratio. So essentially, this red line is the solution to the differential equation. And there is a relationship between the time factor and the percent consolidation. When time is equal to 0, you have 0% consolidation or 0% settlement. And then typically we will use things that correspond to 50% here, and that number is about 0.2. And then another very common number that we use is 90% or 0.9, and then that number is 0.85. Okay? So very often in the problems we try to calculate what is the time that will be required for 90% of the consolidation or of the settlement to take place. So just recall that this is a very important formula. And let me ask you a question here. The question is worded this way. If it takes, looking at this time equation, if it takes 5 years for a 5-meter high embankment to settle, how much time will it take for a 10-meter embankment to settle? So again, if it takes 5 years for a 5-meter high embankment to settle, how much will it take for a 10-meter high embankment to settle? Twice as high. So temptation might be, you know, from just quick reasoning, well, it's going to take twice as long. That's wrong. The answer is, it's going to take the same time. Okay? Why? Because in here, there's nothing that says anything about the loading. In other words, whether you have a very high embankment or a very small embankment, it's going to take the same amount of time. So let me illustrate this. And that will be a question on the short question in the file, or very, very likely. Okay? So what I'm saying is that if you have a case of a settlement, all right, and you have a 5-meter embankment, so that's the 5-meter embankment, 5-meter high embankment. Then it's going to take so much time to reach 90%. If you have a 10-meter embankment, now it's going to settle a lot more. 10-meter high embankment. Now it's going to settle a lot more than the 5-meter high embankment, but it's going to take the same amount of time to reach the same percentage consolidation. Okay, this point and that point are reached at the same amount of time according to the theory. However, if you have a case where the layer is that thick compared to the layer is that thick. So let's say this is H0 and this is 2H0, and let's say we have one-way drainage, although that's not going to make any difference. If it takes 5 years for this embankment to reach 90% consolidation, how long will it take for this one to settle and reach 90% consolidation? Now, the drainage length is proportional to the thickness of the layer, And because the thickness is twice as large here, and you have h squared right there, it's going to take 4 times larger. So if it takes 5 years for this one, it's going to be 20 years for that one. The thickness of the drainage length, the value of the drainage length squared is what impacts the time of consolidation. All right. So I want to do a problem now, problem 26.2. Let me erase this. So problem 26.2. Page 957. When you go to page 957, here we are. An embankment was built as shown in the figure. So let's draw that embankment. We have a layer of clay, and the water table is at the surface. This layer of clay is 5 meters thick. It's clay. And on top of that layer is an embankment made of fill. And this embankment has a unit weight, so it's fill, it's made of sand, and the unit weight is 20 kilonewton per cubic meter. The height of the embankment is 7 meters. So 7 meters. So typical height of embankment approach to a highway bridge. The clay has the following properties. As I said, it's 5 meters thick. It has a C sub C over 1 plus E0 equal to 0.2. It has a unit weight equal to 18 kilonewtons per cubic meter. And it has a coefficient of consolidation C sub V equal to 1.8 10 to the minus 3 centimeters squared per second. And a number of questions. What is the maximum settlement of the embankment? So 1 S max, or delta H max, S max. So this is a case where the consolidation equation will work well, and so we can say S max, and I guess it must say we need to add that this clay is normally consolidated, right? Normally consolidated clay. S max is going to be equal to H0 C sub C over 1 plus E0 log of sigma prime 0 V plus delta sigma V divided by sigma prime 0 V. All right, S max equal. H0 is the thickness of the clay layer. So it's not related to this. This is an issue of the time necessary to reach the settlement. This is the magnitude of the maximum settlement. So H0 is 5 meters. C sub C over 1 plus C0 is 0.2. And then we've got log of sigma prime 0 V. We're going to do all our calculations at the center of the layer, as we always do. because that's what is considered to be representative of what's happening in the layer. So sigma prime OV. So that's 2.5 meters at 18. So 2.5 times 18 minus, and I didn't notice it, but I didn't tell you, but the water level is at the ground surface. Okay? So this is typical of embankments next to rivers. 2.5 times 18 minus 2.5 times 10 because of the water pressure. And I'll take 10 instead of 9.8. I think in the book I took 9.81, but so that's sigma prime OV. Delta sigma V. So there is a lot of load applied by the embankment onto the soil. How much is that load? Well, that load is a pressure P equal to 7 meters of a material at 20, so 720, 140 kilonewton per square meter. So that's P. And we're going to assume that the layer is small enough compared to the width of the embankment. I mean, theoretically, at this point, we'd have to find delta sigma V according to the bulbs of pressure figure that I mentioned in a previous lecture. But to simplify, we're going to assume that the embankment is so large, the B is so large, that 2.5 meters below the embankment, we have the entire value of P. So right here, I'm going to put 140 as the delta sigma, divided by sigma prime OV, 2.5 times 18 minus 2.5 times 10. All right? So I did that, and I found S max equal 0.89. 0.89 meters. 0.89 meters, you know, that's a serious amount of settlement. But these embankments are quite flexible, and as long as you give them time, then they're going to be able to settle eventually. Second question, how much time is required for 90% of the settlement to occur? So question 2 times to 90% of the settlement to occur. All right? So that was 1. T90. Well, we go to the equation right here. Capital T90 times, what is the drainage line? Well, I didn't tell you, but in the problem it says that we have the fill above the clay, and below the clay we have a layer of dense gravel. So right here it is dense gravel. Okay? So because it's dense gravel, the water can actually drain through the bottom of the clay layer, and it can drain up into the fill. Therefore, the drainage length is 1/2 of 5 meters. So here I have T90 times 2.5 square divided by, so let me change this because C sub C, right, C sub V rather, was in centimeters square per second. So to keep the units consistent, 2.5 meter is going to be 250 square centimeter, so 250 square divided by 1.8 times 10 to the minus 3 centimeters square per second. So this is going to be the time in seconds, right here, which I then transform, oh wait a minute, so I'm missing T90 here. So T90 you go to the curve that, let's see, where is that curve? Page 512. So I should make a note of this, that T90, right here, let's write it. Relationship between T90 and percent consolidation, U, page 512. Let me go there to confirm. Page 512. Figure 1734. Page 512. Figure 1734. Okay? So if I go to that curve, which is the normalized curve that I showed you previously, I would find, and I mentioned it, that T90 was about 0.85. So I've got 0.85 times 250 squared divided by 1.8 times 10 to the minus 3. Now that's going to be a big number because it's in seconds. So I got to divide by divide the number of seconds by 60 seconds per minute, 60 minutes per hour, 24 hours per day, and so what did I get the answer in? Oh, I got to go back to page 957 here. 957. 957. Okay, I got it in days, so I can stop here. And then I found that this would take 341 days, equal 341 days. So almost a year for the settlement to get to 90% of this value here of 0.89 meters. Okay. Question 3. How much surcharge is required to get the maximum settlement in 6 months? So you might be working for a Department of Transportation, and then your client said, well, I can't wait 341 days. I want this to be done in half that time. So the goal is to 6 months to reach S max. So to do that, the question is how much surcharge? All right, so the idea is that if you put more load on the on the soil, you're going to be able to speed up the settlement. And you say, well, wait a minute, you just told us that it's independent, the time is independent of the load. So you're right, the time is independent of the load, but the magnitude of the settlement is dependent on the load. The time is not dependent on the load, but the magnitude is dependent. So what's happening is this. We're going to do, let me erase this, to show the curve and why a surcharge is a good idea. Then what we're doing is settlement as a function of time, and then time right here. If I do the test, if I do the the settlement with the fill only, I'm going to have the maximum settlement, and the value was, I erased it, 0.89, so this number here is 0.89 meters. If I put the surcharge, it's going to take the same amount of time, 341 days, to get the final settlement under the surcharge and the fill. So fill plus surcharge. So you see here that, yes, it takes the same amount of time to reach the maximum settlement, but the trick is that while this is 341 days, I can speed up the process because all I want is 0.9, not the maximum value. So right here, I got to find a way to make this 6 months. Okay? So yes, the amount of road that you put doesn't change the amount of time that it takes, but it does change the magnitude of the settlement. And so if you're trying to get 0.9 meters, but it takes 341, you can add a surcharge, and you're gonna reach that settlement much earlier. The question is, how much surcharge do I have to put on top of the fill to be able to get to, so we'll call the surcharge height H. So let's go through that process. The first step in doing that is to calculate T sub V. So first we count T sub U, we call it. So T sub U is going to be T sub U times T sub V over H squared, drainage length. We know that T sub U is 6 months. That's what we've chosen to accomplish. So T is 6 months, and so 6 times 30 days per month times 24 hours a day times 60 minutes per hour times 60 seconds per minute, and now we've got T in seconds times C sub V, 1.8 times 10 to the minus 3 centimeters squared per second, and then H squared, the drainage length is half, so that was 2.5 meters or 250 centimeters squared. I did that, and I got T sub U equal 0.448. Then I can go on the curve that links T sub U and U, and I can read what U has to be corresponding to this 0.448. When I do that, I find U equals 0.732 or 73.2%. This U value is equal to the settlement at 6 months, because I put 6 months here. So it's the settlement at 6 months, which is the settlement of the fill, max, divided by the maximum settlement, S, fill plus surcharge, max. Okay? I know that this value, this one, I computed it already. The maximum settlement of the fill was 0.89 meters. That's this value right there, 0.89 meters. So I know 0.89, I know 0.73. I can back calculate the maximum settlement of fill plus surcharge. So S, fill plus surcharge, max, equals, and by doing this, I found 1.216 meters. So that'd be the settlement if I put 7 meters plus the surcharge that gives me the 6 month for 0.89 meters. But this settlement, this S fill plus surcharge max is also equal to the settlement of the compression of that layer. So that's equal to what we've done before, that is H0. So H0 is 5 times C sub C over 1 plus C0 0.2 times log of sigma prime 0V, and I lost it. It was 2.5 times 18 minus 2.5 times 10, and then plus the delta sigma due to the surcharge and the fill. We had P equals 140 here, and so plus surcharge, we're going to have an increase in load, in pressure, that's going to be equal to H times 20. So the total of the two is going to give me 140 plus 20H divided by sigma prime of V, 2.5 times 18 minus 2.5 times 10. And this quantity has to be equal to 1.216. You can see that, while it's not that pretty, there's only one unknown here, and that's H. So you can back calculate H, and I did that, and I found that H was, what was H? 8.8 meters. So that was the answer to the problem. So I got a 7-meter high embankment. It's pretty high. And I essentially have to double it to be able to speed up the process and meet the deadline of having the maximum settlement at 6 months. And then at that point, I can remove the surcharge. Because if I remove the surcharge, I won't get this, and I'll stay flat, because that's the maximum settlement of the fill. So basically, the settlement process will follow the green line here. So it's we used to do that quite a bit 50 years ago. So, but it's not a very efficient. One of the issues is that with this solution of piling up the soil, this clay may not be very strong, and with that high an embankment, you could create some slope failures here. So that you're solving one problem, but you're creating another one at the same time. So it's not always a good idea. Instead of doing this, what we do today, and remember the magic, this control, this has a huge importance, big impact on time, because it's squared. So if you manage to reduce this drainage length significantly, then you can really decrease the amount of time that it takes for the water to get out of there. So what we typically do today is we put some weak drains. We used to put sand drains, but today we put some weak drains. So we put them vertically, and we make sure they're close together, like this. So each one of those is a wick, and you can see now that the water, which is in the middle between those wicks, only has to go either this way or that way, very little distance, and then go up the wicks and drain in a gravel layer at the bottom in the of the fill. So you reduce from this 5 meter thick with a drainage length, because it was top and bottom, of 2.5 meter, you can reduce this to 0.5 meter, and now you've got 5 times less drainage length, and therefore 25 times less time to reach the final settlement, consolidation settlement. So this is a good illustration of how we use time rate of settlement, and it's a very efficient way for soil improvement, and that's why it's in the soil improvement chapter. All right, one last thing about soil deformation, and that is we need to talk about shrink-swell soils. So everything we've talked about so far has dealt with things going down. Modulus, the birch halifa, the settlement of embankments, everything is going down. But there are cases where when you erode the soil, the structure goes up. And that occurs for relatively light structures. Sometimes they're pretty heavy, but when you are on these soils that shrink and swell significantly, and we've talked about these very active minerals like montmorillonite and smectite, these things that are just like sponges, and you give them water, and they swell dramatically. So I want to talk about two aspects. So let's discuss shrink, swell, soils, deformations. Okay. So we're still within deformations, but now the topic is things that go up and down. And the one plot that I want to show you that's really useful and quite simple is one that links the water content to the shrinking or swelling. And here I'm going to put delta H over H. So this is the strain, remember? And so you can do some, let's say you go to the field, you come back, you have a sample, it's in a Shelby tube, you extrude it, you cut it, and now you have a cylinder about that high, that big around, nice geometric shape, and then you weigh it, and you measure its dimension, the height, the diameter, so you know the volume, and you know the weight. You then let the sample dry on the table, sits there, and you come back an hour later, you weigh it, you measure its dimensions. It has shrunk, if it's made of a material that shrinks a lot. And we do that mostly for fine grain soil because they can't stand up. If you had a sand that fall on the table, and you couldn't do that. So with materials like fine grain material, we can do that. So and these shrink-swell soil are mostly made of fine grain soils. So we have this material, we come back 2 hours later, we weigh it, we measure it in 3 hours, inside the next day, and so on. And then we're able to plot the shrinkage of the material. So we can plot delta H over H as a function of time, and it goes something like this, right? Usually after 24 hours, the material has shrunk almost all it will shrink. That gives us, so you can actually, when you go to the field, the material has zero strain. It hasn't changed in height or dimensions, and it has a certain natural water content. So this is W natural, and this is zero strain. And these are the coordinates of the points at which the test, this shrink test, is going to start. And then as the material shrinks like this, it turns out that it follows a line like this. And then at one point, so you can imagine the particles are here, and you're losing water. You're losing water, losing water, losing water. Now the particles are touching each other, and they cannot shrink anymore. But you can still lose water from between the particles in the pores. So the shrinkage stops, but the water content continues to go down. So right here, and that's a bit of an idealistic behavior. It's not done quite behave that way, but we'll put it straight down, okay? This we call the shrinkage limit, so WSH. We could do the test on the other side as well. In other words, we could put the sample in a bath of water, and then it would swell and swell and swell, but it's difficult to measure the dimension in that case, but you can imagine that we could do that. And if you do that, there is a point, we do that in the consolidation test, where we inundate the sample and we let it swell in the unidirection. There is a point where the sample says, hey, I got all the water I'll ever get, I'm happy where I am. So the sample swells, and it reaches a point where you are at the swell limit. Okay, so this is W swell. This particular amplitude between the swell limit and the shrinkage limit is the shrink-swell index. And this can vary from 5 to, say, 60%. And it's not that difficult to actually create that black line. And if you find yourself at 60%, you're in bad shape, because that's a very shrinking, swelling soil, and you have to be very careful with foundations that you place on them. If you're at 5%, it's not that big a deal, and you probably can live with it. So in other words, that line can reduce in length here. You can go up like this if you have a silt, a relatively clean silt and not very active. But this, if you have, if you're at 60%, then it's a big trouble. You can show that the slope of that line, right here, the slope of that line, if this is 1, this is gamma W divided by gamma D. And I'll call this the shrink-swell modulus. And you can show this is based basically on phase diagram type of analysis. And the other thing is that the material along that black line right here, it remains saturated. In other words, from the swell limit to the shrink limit, the material is full of water. It's saturated, S equal 1. So just because the material is saturated doesn't mean it cannot shrink and swell. In fact, that's where all the action is when the material is saturated. And then you hit the shrink limit, and then you start to lose saturation. And then here, your degree of saturation decreases during that zone. Saturated and then unsaturated right here. All right? Now, if you want to calculate, one thing this is not correct. I need to correct this. This is delta V over V, not delta H over H. So I delta V over V, which usually is about 3 times delta H over H, because delta H over H is one direction, and delta V is in the 3 directions. So this is not a bad estimate of the relationship between the volumetric strain and the axial strain. But so with delta V over V, this is the correct slope. So having said this, you can see that you can calculate, you can essentially write that ESS is the ratio between the change in water content divided by the change in volumetric strength. That's the slope. And in a way, this is a strain, and you can sense that the water content impacts the suction, and the suction is the water stress, and the water stress impacts the effective stress. So you can look at this, if you wish, as if it was something equivalent to a stress strain curve. And so that's why we call it the modulus here, because this, in essence, can be thought of as a stress strain curve model for the shrinking and swelling process. So if I do this, I just wrote here that this is 3 times, so I got delta W, and here I have 3 times delta H over H. And then I also wrote that E sub S was gamma W over gamma D. Okay. You can see that if I have, if I know the thickness of the layer under the foundation, and I know how much the water content is going to change, knowing gamma W and gamma D, I can calculate how much the heave or the swell or the shrink is going to be under that foundation. So I want to finish by doing problem 1715, page 548. So I'm going to page 548. 548. Here we are. So that's what I was writing here. The equation basically is that delta H over H is equal to 1/3, where am I here? 1/3 of delta W times gamma D over gamma W. Okay. And so we're going to use this equation to calculate the movement of a simple case, and that's the case that's in figure 17.5. So problem 1715, problem 1715, page 549. We have a house on the soil, and the soil shrinks and swells. It has a depth, the zone over which this shrinking and swelling is taking place is 3 meters. And we're going to break this into, you'll see the process is very similar to the process of calculating, we're going to divide this 3 meter into 3 1 meter layer thicknesses, and then we're going to have the water content that changes plus or minus 5%. So we'll have a change in water content here, change in water content. So this is 0, and this is W, and here we have 5%. So at that depth, 0.5 meter below the ground surface under the house, the water content during the summer is going to be minus 5%, and during the winter, plus 5%. Okay, on the other side. At that depth, it's going to be 2.5%. So 2.5%. And here it's going to be 1%. Okay. And so we can then calculate how much we can create the same type of plot. And first we have the thickness. So we say 1 meter. 1, 1, 1. This is the thickness in meters here. Then we're going to put the change in water content, delta W. So we said at here it was 5%, so 0.05, 0.05, 0.05. Change in water content. So therefore, from this we can calculate, we know delta W. We're going to take gamma W equals 10. And let's see what I took for gamma D. Gamma D 14 kilonewton per cubic meter. And gamma D 14 kilonewton per cubic meter. So gamma W over gamma D is going to be 10 over 14, 10 over 14, 10 over 14. And then I'm going to do 1/3 delta W to get delta H over H. And so I got 0.0231, so that's delta H over H. 0.0231. So I'm going to have to push over a bit. For the second layer, I've got 0.01155. 1155. And the third layer, I have 0.00462. So I multiply by 1,000 to get it in millimeters. So delta H in millimeters is going to be 23.1, 11.5, and 4.6. And then the total movement here, the swell or shrink, is going to be the sum of this. So how much is that? 34, 38, 39.2 millimeters. So that means the edge of the house is going up that much. And we could do it again for the center of the house, because in the center of the house we have less movement, and that's why that's going to actually bend the house. So we'll stop here, and then next time we'll talk about foundations and what are the good types of foundations for these light buildings. Okay.